question, we're asked to find the domain of some functions that combine two other functions. And before we do that, it would help if we found the domains of the given function. So first of all, notice that f of x, which is 1 over the square root of x, you can put any value in for x except for 0 and anything negative. So that means that x has to start at 0, or actually can't include 0, but start at 0, not including it, and go greater. And so the domain of f could be written like that, or in interval notation, that would be from 0 to positive infinity. Now let's look at the function g of x, which is x squared minus 4. The domain of g is going to be all real numbers. There are no restrictions for that one, because if you plug anything in for x and you square any number, you always get back a real number. And if you subtract 4 from any real number, you get another real number. So there's nothing that's going to make the function undefined. Whereas with f, remember, if we had plugged in, say, 0 for x, then we would have the square root of 0, which is 0, and then 1 over 0 is undefined. So that's why we include 0. And likewise, we couldn't include anything negative, because if x were allowed to be -1, for example, you would have 1 over the square root of -1, and the square root of -1 is not real. Okay, so we can't allow that either. We're looking for only things that produce real numbers. All right, so now that we figured out the domains of each of the functions on their own, let's look at these composite functions. Or actually, there's one quotient function here and two composite functions below it. So the quotient function is dividing f of x divided by g of x. And we don't worry too much about what's in the top, but we definitely want to avoid having 0 in any denominator for the same reason I described above. We know that 1 over the square root, any number divided by 0 is undefined. So we want to look out for that. Now also, whenever you're combining two functions together, you have to make sure that all the x values you might plug in will work for both functions. So that means you have to find the intersection of the two domains where they both agree and they will both work for both functions. So we can start with the larger domain, which is for g, because there are no restrictions. It actually goes the whole number line. Now, the domain of f is restricted, though, starting at 0 and going positive. So that means that we cannot use anything except where they both agree or intersect or overlap. And so we are starting with just the domain of f as our beginning point for the quotient function. Or not our beginning point, but you know, where we start from. So we're going to start at 0 going greater than 0. Okay. Now, from that, we may have to restrict a few values, because we have to look out for g of x and make sure that it will never equal 0. So then how do we ensure that? Well, we can take the function x squared minus 4 and set it so that we say it's not equal to 0 and solve for x. So then using the square root method, we can add 4 to both sides, take the square root of both sides, and don't forget the plus minus, and we figure out that x shall not be allowed to be plus or minus 2, because that would create an undefined result in our overall quotient function, because that would mean 0 in the denominator. So now we know that both +2 and -2 are off limits. So -2 isn't a problem. It's outside of our blue region that we identified. So we don't have to worry about -2, but we do have an issue right here at +2 where we have to have a hole so that we're not going to use the x value of 2. So that means that our domain will start at 0 but not including it, and continue up to +2 but not including it. Then we'll kind of hop over or swing under +2, start again on the other side of it, and go towards positive infinity. So that's the answer to the first of these three functions down here. The domain of the quotient function f over g of x is from 0 to 2, union with 2 to positive infinity. Next, we'll do the domain of our first composite function listed here, f of g of x. Now, let's begin by actually composing the two functions to see what it looks like. That'll help us visualize what we need to do here. So when you compose two functions, starting with the outer function, this is how I always do it. So the outer function says it's f, right? So let's start with f. Okay, now we'll come in and remove the x from there, and in its place, we're going to put g of x. So g of x was x squared minus 4, right? So now we can see that we have a couple of potential problems down here. Again, we cannot let 0 be in the denominator, and we also cannot allow any negatives underneath the square root. So being that we can't allow 0 and we can't allow negatives, then we should have x squared minus 4 restricted so that it is always greater than 0. Now, being that it should be greater than 0, we can solve this like we did before, adding 4 to both sides. But after that, we have to be extra careful because now it's saying that x squared has to be greater than 4. So that means that even negatives have to be a certain distance away from 0 for that to happen. Because when you multiply negatives together, you're going to get a positive, right? So if you can picture it on a number line, it makes more sense. Let's say we're here. This is our x number line. Remember when we solved before, when it was an equal sign, we got that x had to not be, if we were trying to keep x not equal to 0, then we said x could not be -2 or +2, right? So let's put those on the map here, -2 and +2. All right, so we already know that we should not allow that to happen because we don't want 0 in underneath the square root. But also, it's not just those values that would be problematic. If we came in the middle here, and any value that you pick, let's say we picked -1. If x was equal to -1 and then we squared it, then -1 squared would be +1, and +1 is not greater than 4. So what we really need to do is get at least as far, like farther away than -2, away towards the negative infinity side, or farther away greater than 2. All right, so on the number line, that means we would start at -2 but not including it and go to the left, and at +2 but not including it and go to the right. And all the x values in those regions would be okay and not cause an undefined result in our composite function. So we will write this using interval notation. We'll start with a parenthesis going from -2 backwards towards negative infinity, and a parenthesis starting at +2 and pointing towards positive infinity, +2 and pointing towards positive infinity, and then we're going to union those to create one domain, one set of numbers. All right, so from negative infinity to -2, union from +2 to positive infinity. All right, now finally we have one more to do, one more composite function down at the bottom there, and they've reversed the order. So now f of x is the inner function, and we know that f of x has a restricted domain. So since we're worried about the inner function first, because if that doesn't work out, then we can't continue and work our way out. So we got to start with the domain of f. Starting at 0, we cannot include it, but we can move to the right towards positive infinity. Now within that, are there any issues for the outer function g of x? In other words, is there any value that could be produced by plugging values of x into f? Are there any f values, any function values that when plugged into g of x are going to create a non-real number result or something that's undefined? Well, remember the domain of the outer function g is unrestricted. So really any real number can go into g and there is no problem. And since we are already making sure that only real numbers will get plugged in because we're using the domain of the inner function, then we're set and safe. As long as we stick to values that work for f, then it'll be just fine for g. All right, so our answer for the domain of g of f of x is the same domain of the inner function, which is 0 to positive infinity.